What is up, everybody? Welcome to the 11th lecture of Contemporary Math. Today we're going to be talking about chapter 11.5 through 11.7. To start off with, let's talk about permutations, let's talk about probabilities with permutations. Let's consider this example that I've got written up here. We've got a bag full of 100 marbles. Every marble is numbered 1 through 100. So we've got marble 1, marble 2, so forth and so on. And the bag has been shaken up fairly well, right? Well, we want to answer the question, what is the probability of pulling out 5 marbles such that the first marble has a single digit on it, and the last marble has a single digit on it? Okay, well, if that's the case, if this is what the question is, then our sample space is going to be the space of permutations of 5 marbles out of 100. That's pretty obvious, right? We're pulling out 5 marbles out of 100. There's going to be 100 pick 5. Number of possible ways to do this. In the event that we're interested in, it's the event such that the first and the fifth marble has only 1 digit on it. Okay. So how are we going to do this? Well, first we can start by finding the number of possible ways our sample space can occur. By finding the size of our sample space. Well, it states itself pretty clearly here. It's permutation of 5 marbles out of 100. So that's going to be 100 pick 5. Which is, as you can see, a giant number. 9,034,502,400. Giant. A lot of different ways that can happen. And that makes sense, right? Like, we're picking 5 of these out of 100. Of course, there's going to be a bunch of different ways we can do that. So the next thing we need to do is figure out the size of our event. Well, how many different ways can that event happen? So to do that, let's consider what's happening over here. The first marble we're choosing is going to be from marble 1 through 9, right? Those are the only 9 marbles we can choose from, because those are the only 9 that have a single digit on them. Same with this last marble, right? Well, if that's the case, there's 9 different ways we can pick that first marble. And 8 different ways we can pick that last marble. So what about the 3 marbles in between? We're going to reserve 1 marble for the first and 1 marble for the last, right? So out of the 100 marbles, 2 of them are automatically reserved. Meaning, we have only 98 choices that we can make, choices that we can make here. So 98, we just picked a marble. So 97 choices here, and 96 for our 4th marble. So notice the number of ways to pick our 1st and 5th marble. This is going to be 9 pick 2, which is 9 times 8. Actually, let me write it a slightly different way. Factorial of 9 over 9 minus 2 factorial over 7 factorial, which is equal to 9 times 8, or just simply 72. So there are 72 different possible ways to pick our first and last marble. What about our middle 3 marbles? Well, that's going to be 98 pick 3, right? And that's a huge number. I'm not going to try to write it out. So together, what this means by the fundamental principle of counting is that the number of ways our event can occur is going to be nine, pick 2, times 98, pick 3, which is equal to 72 times 98, pick 3. Again, giant numbers, I'm not writing them out. All right, cool. So we know the size of our sample space and we know the size of our event space. Now what? Well, now we calculate the theoretical probability. Theoretical probability is the size of our event space divided by the size of our sample space. So, writing that all out. So writing that all out, excuse me, what we've got is the probability of picking 5 marbles such that the first marble has 1 single digit on it, and the last marble has a single digit on it. The probability of this occurring when choosing 5 marbles out of 100 is 9 pick 2 times 98 pick 3 divided by 100 pick 5. And this is really just an example of calculating probabilities with permutations. All we've done here is we've said the number of events is a permutation. The size of our sample space is a permutation. So we use those permutations to calculate the size of both sets, and then use that to calculate our probability, just like we normally would. All right, so let's look at doing the same thing, but this time with combinations. To talk about probabilities with combinations, let's imagine ourselves back at the ice cream shop. We go to the ice cream shop to pick up a sundae for ourselves and for a friend. We get there though, and we realize we forgot what the order was that our friend wanted. And we sit there and we're like, should I call him, should I not call him? Well, let's find out what the probability is of us guessing the order right. So at the sundae shop, any given sundae that we can order has to have has a choice of 3 out of 15 flavors. And we have a choice of 5 different toppings. Okay, So we can choose 3 out of 15 flavors and 5 different toppings. If that's the scenario here, then the event is just the single right order, right? It's the one order that's what we actually want to get. For the sample space, in this case, it's going to be the combination of 3 flavors and 1 topping. All right, well, cool. We already know what the size of our event space is. It's just 1. That means we need to find out what the size of our sample space is. Well, like we say here, it's a combination of 3 flavors. So it's 15, choose 3. So we gotta choose 3 different flavors out of 15. That's going to be what we're doing. Then that is 15, choose 3, which is equal to 15 factorial divided by 15 minus 3 factorial times 3 factorial, which is equal to 15 factorial times 12 factorial times 3 factorial, or 455. There are 455 different ways of choosing just 3 ice cream flavors alone. All right? We also have 5 different toppings that we can choose from. So to find out the number, or the size of our sample space, because of the fundamental principle of counting, we have to multiply 455 by 5, right? There's 455 different ways of choosing the 3 ice cream flavors, and 5 different ways of choosing our single topping. So the size of our sample space is going to be 5 times 455, which is 2,275. And since the probability of choosing the right single order is the size of our event space divided by the size of our sample space, that means the probability of choosing the right order, since you forgot it, right, is going to be 1 divided by 2,275. In other words, you should probably pick up the phone and call your friend before you mess up their order. Because there is 1 in 2,275 for a probability of getting the order right. That is crazy. That is less than 1%. Less than 1% chance of getting it right. Alrighty. So we've gone over now probabilities with permutations and with combinations. What's left? Next we're going to talk about not and or. To talk about the probability of not E, we first need to talk about what's called the complement rule of probabilities. What the complement rule of probability says is the probability of E plus the probability of not E, together they're going to add up to 1. Having said that, we usually don't write not E. We usually use the typical set notation with a sort of apostrophe there. So we have E apostrophe, and it means the same thing. What this tells us, though, is that the probability of not E, it's going to be equivalent to 1 minus the probability of E. And all we have to do is rearrange the arithmetic there, right? And we can find that. So using that last example really quick, we found that the probability of E was equal to 1 in 2275. So if we're going to find the probability of not E, so in that last example, the probability of ordering the wrong thing, that's going to be one minus 1 over 2275. Or 2274 and divided by 2275. So there's a high probability there that you're going to order the wrong thing. All right. Having said that, what about the case of saying, I want to know the probability of A or B happening? How do we handle that? First, to handle that, we need to know that if A and B are mutually exclusive, then what we're saying is there's no way that A and B could occur together. And because of that, the probability of A or B is really just the probability of A plus the probability of B. And this is in the case that A or B, or A and B, I should say, are mutually exclusive. They don't have any overlap in events. We oftentimes write this as A unioned with B. Same idea. So to look at an example of this, let's say we want to know what the probability of picking either a king or a queen out of a deck of 52 cards is. Well, notice if I pull a king, there's no way I'm going to pull a queen. And if I pull a queen, there's no way I'm going to pull a king. So these two events are mutually exclusive. So because of that, the probability of pulling a king or a queen is the probability of pulling a king plus the probability of pulling a queen. The probability of pulling a king is 4 out of 52. And the probability of pulling a queen is 4 out of 52. So the probability of pulling a king or a queen is going to be 4 out of 52 plus 4 out of 52, which is equal to 8 out of 52, and we can reduce this further. So, because this definition can be a little weird, I want to show you all in just a second, well, let me step back even further than that. We'll see in just a second what it means to not be mutually exclusive, and I think that'll clear up a little bit what it means to be mutually exclusive. So, to better explain this idea of what it means for two events to be mutually exclusive or to not be mutually exclusive, let's look back at what it means to be an event, or even a sample space. Recall, a sample space is the set of all possible outcomes. An event is a subset of that, right? So if we want to know the probability of two different events occurring, we have two different subsets of our sample space that we're considering. In the case where those two different subsets have no intersection, that's the mutually exclusive case. In the event that they do, or in the case that they do have an intersection, then they're not mutually exclusive. So as an example of this, let's say we've got a set of numbers 1, 2, 3, and 4. The subset of that, which is even, would just be 2 and 4. And the subset, which is prime, would be 2 and 3. And if we wanted to know the number of all, the size of the combination of those two sets, or those two subsets rather, we would add their sizes, their individual size, together and subtract that intersection. And in that same way, we're going to do something very similar with probabilities. In the event that A and B are not mutually exclusive, the probability of A and B would be the probability of A plus the probability of B minus the probability of their intersection. Having said that, we usually write P, the probability of A and B, as the probability of A intersected with B. And if we think about what we're doing here, really it's the same thing as saying, what's the size of the two sets together? That's all we're doing, really. And then dividing that by the size of our sample set. All right, so enough of this. Let's look at an example here. The probability of pulling a face card out of a deck of 52 cards. It's 12 and 52. The probability of pulling a diamond, well, it's 13 out of 52. But notice, 3 of those face cards, they are diamonds, right? So we have to remove those so we don't overcount them, so we don't count them twice. And that's really what we're doing with all of this. We're saying, hey, these two things have something in common, we don't want to count it twice, so let's go ahead and remove it. So here, to find the probability of pulling a face or a diamond, we have to add the probability of pulling a face to the probability of pulling a diamond, to the and subtract the probability that the card we pull is a diamond face card. What that looks like now is 12 out of 52 plus 13 out of 52 minus 3 out of 52 is equal to 22 out of 52. So this is really the idea of it all. We're really ultimately saying, I want to know the probability of pulling something out of these two giant sets combined. But if I count each set individually, their intersection is getting counted twice, so I have to pull it out. When I pull it out, it's going to be the probability of the two that I'm pulling out. That's all we're doing, really. Having said that, let's move on to the case of P and B. So mutually, I shouldn't say mutually, I should say, so independent sets, independent events. Things like this happening and then this happening, as opposed to, well, you'll see what I mean. All right, so obviously if we're talking about independent events, next we're going to talk about dependent events. A dependent event is just, or dependent events, I should say, are really just events that influence one another. And if A and B are both dependent, then the probability of A and B is the probability of A times the probability of B given A happened. And usually we write this using this notation here. And this is called a conditional probability. We'll talk more about that in just a minute. But for now, just know that if I use this notation, it just means the same thing as this. So let's look at an example. Let's look at two examples actually. We want to know what the probability of pulling an ace and a face card is. Well, the probability of pulling an ace, there's only 4 aces, 52 cards, so the probability is 4 in 52. But if I pull an ace, that means there's one less card in the deck. So instead of 52 cards, there's now 51 cards. So the probability of pulling a face card, given that I've already pulled an ace out, is going to be 12 and 51. So the probability of pulling an ace and a face is going to be 4 over 52 times 12 over 51. So that seems pretty straightforward. What about pulling 3 hearts? How would this problem work out? Well, we have 3 different conditions that are happening, right? Pulling the first heart, pulling the second heart, given that we pulled the first heart, and pulling the third heart, given that we pulled the first 2 hearts. So, pulling the first heart, well, there's 13 cards in that entire suit. It's going to have a probability of 13 and 52. Well, we just pulled 1 heart. And 1 card, right? So there's 1 fewer hearts and 1 fewer card. Actually, really quickly, let me correct a typo that I just wrote on the board. What I should have written is the second card given the first, and the third card given the first and second. Typo, and I apologize for that. Having said that, there's a lesson to be learned. All of us make mistakes. I just made one on the board, right? So don't beat yourself up if you make a mistake. In fact, usually means you're learning if you're making mistakes. Lean into them. They're a good thing. But that's neither here nor there. Let's get back to this problem. So, we're pulling 3 hearts. So, pulling the first heart, and the second heart, and the third heart. Pulling the first heart, because there's 13 hearts in the entire suit, and 52 cards as a whole, then the probability of pulling that first heart is 13 divided by 52. Pulling the second heart, well, again, like I started to say before, there's now 12 hearts and 51 cards. So, this is going to be 12 divided by 52. Or I mean 51, my apologies. And pulling that third heart, given that we pulled the first and the second, well, that's going to be 11 and 50. So that means the probability of pulling all 3 hearts is going to be 1352 times 12 and 51 times 11 and 50. move on then to conditional probabilities. Let's talk about those. Getting back now to conditional probability. What a conditional probability is, other than just this term here, right? Like whatever this term means. What it really means is if we're going to restrict what's available for B to happen, what's that probability? So when we say the probability of B given A, we're saying we're restricting our case to the event that A has happened. But we want to find the probability of B. And to do that, we use the following formula. The probability of B given A is equal to the number of shared events between B and A divided by the number of events of A. Okay, so let's look at an exact example. We want to know what the probability of pulling a number card is, given we restrict ourselves to red cards. So I've got this deck above me. We can see really quickly, restricting ourselves to just number cards, to just red cards, restricts us to just these up here. Now, we want to look at the intersection between the red cards and the numbered cards. So the numbered cards would be all of these right here, right? Meaning that this intersection of the two, well, that's these right here. So that means there are 18 different shared outcomes between the two sets. So we can say an A intersection with B is equal to, we know that this is, well, let me step back. We know this probability is going to be equal to the number of cards in that intersection divided by the number of cards, or the number of outcomes to A. And we know that this intersection, based on what we've drawn up here, has 18 cards. So the question now is, which one of these two sets, A, is the set circled in yellow, set A, or is the set in pink, set A? Well, A represents the red cards, so it would have to be this, right? So how many outcomes are there possible there? Well, there's going to be 26. It's half the deck. So the probability of pulling a numbered card, assuming we restrict ourselves to just red cards, well, it's going to be 18 out of 26. The way we found that was, we said, all right, all the red cards, that's up here. All the number cards, that's these right here. What do they have in common? What is A intersection B? Well, it's just these 18 cards here. So the number of elements in that intersection, the number of possible outcomes, must be 18. And because the red cards were our set A, the number of outcomes for it must be 26. And this is generally the idea of calculating probabilities for A given B, B given A, however it's presented to you in this particular case, right? having said all of that, if you have any questions, by all means, shoot me an email. In the meantime, have a good one, guys.